So friends, today we are going to discuss a design of square footing. Okay, in this there are 6 steps involved. The first step is depth of foundation. Okay, we have to determine the depth of foundation. Second step is base area calculation. Third step is determination of depth of slab using one-way shear. Fourth step is check for two-way shear. Fifth step is check for bending moment. And the last step is check for developmental length. So next we are going. So friends, this is a previous year university question. And the question is, design a square footing of isolated column having size 400 by 400 carrying 2100 kilonewton load. Safe bearing capacity of soil is 280 kilonewton per meter square. Use N20 and Fe415 steel. Check for one-way shear and two-way shear. Also, we can use IS 456 2000 code. Okay, we have already discussed the steps we have to follow in this design. So the first step is depth of foundation. We have to determine the depth of foundation using the equation dF is equal to SPZ divided by gamma into 1 minus sin phi divided by 1 plus sin phi the whole square. Okay, the SPC is given in the question as 280. Okay, divided by gamma. Gamma is the unit weight of soil, that we take it as 18. And phi is the angle of repose, that we are taking as 30. So substituting these values in the above equation, we will get dF is equal to 1.8 meters. Step 2 is base area calculation. So in the question, the load on column is given as 2100 kilonewton. Assume 10% extra for self weight and overburden. Total load becomes 2100 plus 2100 into 10 by 100, that is 210. We have to add both of them, we will get 2310 kilonewton. Then base area required is equal to total load divided by SPZ. Total load is 2310 divided by SPZ is 280. Okay, then we will get it as 8.25 meter square. So we have to take its roots. We will get 2.9. That is assuming a square base. We are assuming a square base of 2.9 into 2.9 meters. Actual soil pressure on the base equal to a load on column divided by base area. Load on column is 2100 divided by base area. That is 2.9 into 2.9. We will get as 249.70 kilonewton per meter square. Step 3. Determination of depth of slab using one-way shear. Okay. Consider a section at a distance of D from the base of column. This is the column base and we have to consider a distance of D. The distance will become 1.25. That is 2.9 divided by 2. 2.9 divided by 2 minus 0.2, this half. Okay, then we will get it as 1.25, and then and this distance is 1.25 minus D. Shear force is equal to this shaded area into this actual soil pressure on the base, that is 249, into factored value, that is 1.5, factor of safety 1.5. So shear force become 1.25 minus D into 2.9 into 249.70 into 1.5. Okay, area restricting one-way shear is equal to this portion. This is 2.9. Then 2.9 into D. D will be this distance. Then shear stress will be equal to shear force divided by area restricting one-way shear. shear stress is equal to, that is substituting these above values in the equation, we will get this, and for M20 and tau C minimum, that is in IS 456 2000, the value of tau C minimum for M20 is 0.28 Newton per mm square. That is from page number 73. Okay. So from page number 73, table 20, maximum shear stress. Okay, tau C minimum. Sorry, it is not table 20, it is table 19, that is tau C minimum. This one. For M20, it is for M20 the minimum value is 0.28 Newton per mm square. Okay, so all other values are in kilonewton per meter square, so we have to convert it into kilonewton per meter square, so into 10 raised to 3. Okay, then after solving we will get D as 0.715 meters, or D is equal to 715 millimeter. Assume a cover of 80 meters. Okay, we have to assume a cover of 80 meters, then capital D will become small d plus cover, that is 715 plus 18, that is 795 mm. Fourth step is check for two-way shear. Okay, the two-way shear or punching shear, that is, it is acting at a distance of d by 2 from the base of column, that is from base of column there is d by 2 distance. Okay, so the punching shear force become this shaded area into actual soil pressure on the base into 1.5. Okay, so we have to find the shaded region. So for that, this is 2 square. Okay, one is having greater dimension and one is a smaller dimension. So square having greater dimension, that is 2.9, its area is 2.9 into 2.9, that is 2.9 square, minus this small square, that is 1.15 square. Okay, we will get the shaded area, and into 249.7, that is actual pressure, into 1.5, we will get it as 2684.3098 kilonewton. Area resisting punching shear is 4 into 1 point, that is this distance is 1.115. okay, 4 into, there are 4 sides, that's why it is 4 into 1.115 into 0.795, this value is D. Okay, capital D, this value. So we will get as area restricting punching shear is 3.5 meter square. So punching shear stress is equal to, that is punching shear stress is equal to punching shear force divided by area restricting one-way shear. Okay, we will get it as 0.766 Newton per mm square. Then from page number 58, from IS 456 2000, page number 58, article 31.6, page number 58. Okay, here permissible shear stress, this one. Okay, it is when shear reinforcement is not provided, then the calculated shear stress at the critical section shall not exceed Ks tau C value. Okay, from this code, Ks value is 0.5 plus dc, and but it should not be greater than 1, and tau C value is 0.25 root fck. Okay, so that is Ks is equal to 0.5 plus BC, it should not be less than 1, and BC is short side divided by long side. Here it is a square column, that's why both are same. There is 0.4 divided by 0.4, which is equal to 1, and Ks is equal to 0.5 plus 1, that is equal to 1.5, but it should not be greater than 1, so we assume it as Ks is equal to 1, and tau C is equal to 0.25 root FCK, and 0.25 and FCK is 20, so we will get it as 1.118, and Ks tau C value we will get 1.12 Newton per mm square. Okay, so 0.766 is less than 1.12, so it is safe in punching shear. Okay, the punching shear stress is less than Ks tau C value, so it is safe in punching shear. The fifth step is check for bending moment. So the critical section for bending moment is located along the face of column. That is, there is no D distance to take. It is from the face of column. That is, shaded region is this complete. So, and this distance is 1.25. Factored bending moment, there is 1.25 into 2.9 into 249.7 into 1.25 divided by 2 into 1.5. Here it is bending moment, that's why we are taking divided by 2, and we get a factored bending moment as 848.59 kilonewton meter. Okay, then check for depth. Mu limit is equal to 0.138 FCK BD square, and Mu limit is this one, 848.59 into 10 raised to 6, which is equal to 0.138 into 20 into 2900. B is 2900, this distance, into D square. Okay, so D required will be equal to 3 to 5.60 millimeter, and we have D provided is 715 millimeter. So the D provided is greater than D required, so it is safe. Next is area calculation. Mu is equal to 0.87 Fi AST D into 1 minus AST Fi divided by BD FCK. This equation is provided in IS 456-2000 in page number 96. So no need to by heart. Okay, this is page number 96. This equation is this, and we have to find AST. Okay, substitute all other values. Fi we have 415, and D is 715, B is 2900, and substituting all these values we get AST as 3402.918 millimeter square, providing 10 mm diameter bars. So n into pi by 4 into 10 square is equal to AST, that is 3402.918. We will get n is equal to 44. Okay, then spacing is equal to 2900 divided by n. Okay, we will get 65.9, which is less than 3D or 300 mm, so it is safe. So provide 44 numbers 10 mm diameter bars at 66 mm center to center. And the final step is check for developmental length. LD required for 10 mm diameter bars is 5. And this equation is given in page number 42 in IS 456-2000. Page number 42. Okay, this one. This is the equation. Development length for bars. LD is equal to 5 sigma S divided by 4 tau BD. Okay, phi is the nominal diameter of bars. we are taking 10 mm diameter, so I will be 10. And top BD, the value of top BD is given in the next page. It is in this page number 43. Top BD for M20 it is 1.2, and in the code for it is given that for default bars conforming to IS 1786, these values shall be increased by 60%. So it should be increased by 60%. So we are taking multiplying it with 1.6. Okay, then we will get LD required as 470 mm. LD provided is 1250 minus 80. 80 is the cover, and so it is greater than LD required, so it is safe.